Okay, we're going to look at some numerical methods for finding roots. So the trapezium rule is an example of a numerical method, and you use that to find an approximation for the area under a curve. What we're going to do now is we're going to look at three methods for finding roots of functions, and they really come into their own when you can't find the root algebraically, or you want to get a decimal approximation to the root to whatever degree of accuracy you want. So you can just continue the method until you get as close to the root as you want to be, depending on the situation. This first method is called change of sign, and this is kind of your textbook definition. So if f of x is continuous on the interval ab, this ab, I think I've shown you this before, just in case, this means that a is less than or equal to x is less than or equal to b. If you have an open bracket, that means a less than x less than b, but you'd be specifically talking about an interval there, obviously, and not some coordinates. So if f of x is continuous, that means it has no breaks. So between a and b, you just have a smooth curve with no breaks. Something like y equals 1 over x. So I'm kind of trying to talk and talk a little bit. So something like y equals 1 over x, which looks like this. Chalk and talk and not so much. That is discontinuous at x equals 0 because there's a break in the curve. So this method requires the function to be continuous on the interval ab. If f and a of a and f of b have opposite signs, then f of x has at least one root alpha where a is less than alpha is less than b. So nice straightforward example to start with. We've got f of x equals x cubed minus 4x squared plus 3x plus 1. Show that f of x has a root between x equals 2 and x equals 3. So this is a continuous function. A cubic has no breaks in it, so you don't need to worry about any discontinuities. And I need to plug in 2, so you do f of 2, and that equals 2 cubed minus 4 times 2 squared plus 3 times 2 plus 1. So I'm just plugging into there. That gives you minus 1, which is less than 0. You need to write in this less than 0 to show your understanding. And then I do f of 3. So I'm just mimicking this. So I'm plugging in 3 cubed minus 4 times 3 squared plus 3 times 3 plus 1, and that gives you 1, which is bigger than 0. And so we've got a change in sign in f of x. You need to write a few words here, sort of conclusions to pick up your last mark. So change in sign in f of x. You could write and f is continuous. You won't get a mark for that on A level, but yeah, you need to just check f of x is continuous. And the root is therefore between x equals 2 and x equals 3. So you must write that conclusion in as well to show your understanding. So all you're basically saying, I'll just take this messy bit off that's bugging me, being a perfectionist. So all you're basically saying is that between 2 and 3, f of x is going from being negative to positive. So the value of the function here is negative. The value of the function here is positive. We're not really interested in the shape in between, but that if it's going from being negative to positive, there must be a place in between where the value of the function is 0. Similarly, if it was, which it isn't in this case, but if it was going from being positive to negative, like that, then there must be a place where the function equals 0, and that is your root in the interval. Just check how much time I've got on this one. Right, I will do the next board, I think, now. So, drawbacks of this method. So all these methods have drawbacks. So these are kind of scenarios where the method can fail. So the first one is if you have an even number of roots between A and B, then you will end up in this sort of situation. So when you do f of A for this graph, it's less than 0. And when you do f of B, it's less than 0. And the method will not pick up any roots, even though there are actually 2 roots between A and B. Similarly, if your roots are all grouped closely together, so for instance for this cubic, f of A is less than 0, f of B is bigger than 0, but there is more than one root in between the two, so you could have an odd number of roots between the two. The method won't actually tell you how many roots you have. All the method is telling you is that you have at least one root between A and B. In this case, there's 3, so it's not ideal in that sort of scenario. And if f of x is discontinuous on AB, so for instance here we've got this asymptote, so there's a discontinuity, then f of A is bigger than 0 here, f of B would come out as being less than 0, and so the method would tell you there's at least one root, but actually there's no roots, there's a discontinuity and an asymptote. So the method will only work if f of x is continuous on the interval AB. So they're just little things to look out for, but the main way you'll be using this method, and you'll be using it in all the questions throughout this topic, is to show, anytime you're asked to show there's a root in an interval, you do change of sign, and you need to lay it out like that. And I'll leave you with that board in case you want to use it.